Hello students, I am Satitrakar. Welcome to Cars Physics. We are continuing work, power and energy. In this lecture we will discuss a beautiful concept, that is equilibrium. Equilibrium. We will discuss different types of equilibrium and conditions for equilibrium and conditions for different types of equilibrium. Of course, we will know how to get position of different types of equilibrium, and accordingly we will some few numericals on the basis of the concept or discussion. Okay. Then equilibrium, as we know, the general condition for equilibrium is net force or sum of forces or resultant force acting on a particle or acting on a body must be equals to 0. Suppose a number of forces are acting on a body or a number of forces are acting on a particle, then the body or the particle will said to be in equilibrium if net force or resultant force acting on a body is 0. This is basic condition. Okay. Again, what we know? Work done by conservative force. Work done by conservative force defines change in potential energy, and work done by all forces. Work done by all forces means conservative, non-conservative, internal, external, etc. Work done by all forces define change in kinetic energy. So work done by conservative force defines change in potential energy. Okay. Then potential energy means change in potential energy. As we know, we can't define directly potential energy, but we do define change in potential energy. To know potential energy at a given point in a field, we have to take a reference point where potential energy is 0. Okay, so potential energy at a point in the field minus potential energy at reference point, that is 0. So this is change in potential energy. We do name it potential energy, but practically we do define change in potential energy. Okay. Then potential energy or change in potential energy is equal to negative of work done by conservative force. Negative of work done by conservative force, we have discussed in this concept in previous lectures. Okay. Then small change in potential energy. Small change in potential energy is equal to small work done by conservative force. Again, negative of work done. Negative of small work done by conservative force. It's okay. So this is change in potential energy, small change in potential energy, small work by conservative force. Okay. So change in potential energy is minus work done by conservative force, small work. So conservative force dot displacement, and that's equals to du is equal to minus fds cos 0 degree. Displacement is along the direction of force. Okay. Then du is equal to minus f is conservative force into ds means conservative force. Expression for conservative force is equal to minus du by ds. So expression for conservative force is equal to minus du by ds in the algebraic form. Okay. So du by ds, you just see, if you plot a graph between change in potential energy, let's take along a y-axis, and change in displacement, let's take along x-axis, then du by dx. So du by ds is slope of graph between u and s. So du by ds is slope of graph u versus s. Potential energy versus displacement. So force is equal to du by ds, means conservative force is equal to slope of graph u versus s. Expression for conservative force is equal to minus du by ds. So du by ds is slope of graph between potential energy and displacement. This is your basic concept. So this is equals to slope of graph. Slope of graph u versus s. Is it clear? Okay. Then can I erase it now? The basic condition, resultant force or net force acting on a body is 0. Then this is expression for conservative force. See, if we consider force along x-axis, force may be resolved into 3 rectangular components. In terms of rectangular components, force along x-axis may be taken as partial derivative of potential energy with respect to x, because we do only consider along x. So this is partial derivative of potential energy with respect to x. Similarly, force along y-axis, conservative force, may be taken as minus du by dy. Force along z-axis is minus du by dz. Of course, you can express it in vector form by taking I cap, j cap and k cap. Is it clear? Okay. This is about expression for conservative force in terms of slope of graph between potential energy versus displacement. Is it clear? Is it okay? Fine. Then we will go to different conditions of equilibrium. Now I am erasing it. Types of equilibrium. Types of equilibrium. See, for any equilibrium, any type of equilibrium, for any type of equilibrium, net force or resultant force acting on a particle or acting on a body is 0. Is it clear? Again, since force is minus du by ds, or if you consider along x-axis, then you may take du by dx. Then if f is 0, then minus du by dx is equal to 0. So these are two basic conditions for any equilibrium. For any equilibrium, these are the basic conditions. Resultant force is 0 and slope of graph between potential energy versus displacement is also 0. Then we will go to, I am writing here the other condition, minus du by dx. I am considering x-axis is equal to 0. You may consider y-axis, z-axis, or in general minus du by ds. Is it clear? Fine. Okay, these are two basic conditions for any equilibrium. Then we will go to type of equilibrium. Type of equilibrium: stable equilibrium, stable equilibrium. Then comes unstable equilibrium, and finally neutral equilibrium. Okay, these are 3 types of equilibrium: stable equilibrium, unstable equilibrium and neutral equilibrium. We will study how do we decide whether a body is in stable or unstable or at neutral equilibrium position. Okay, stable. We'll understand it. Okay. To have better understanding, let's consider this is a hemispherical bowl. A hemispherical bowl, and this is ground level. Means that suppose a body is placed at the bottom of hemispherical bowl and mass of the body is m. Mass of the body is m. See, weight of the body acts in vertically downward direction and normal reaction is R, and as it is observed, weight and normal reaction are in opposite direction, so they balance each other. So in this case, resultant force or net force on the body is 0. So the first condition for any type of equilibrium is satisfied. Is it clear? Okay. Then force is equal to slope of graph. Force is equal to slope of graph means here also du by dx is equal to 0. Means how to do? Slope of graph is 0. We know du by dx is equal to tan theta. Slope means theta should be 0 degree. Tan theta should be 0. To have 0 slope, just draw a tangent at this position. See, for this elemental distance, tangent is parallel to this surface. So here theta is 0 degree. Okay. Then du by dx is 0. Is it clear? Okay. Then for unstable equilibrium, we will discuss gradually. Let's consider a hemispherical bowl is placed like this in inverted position. Okay, and here there is a body. Here there is a body. Mass of the body is m. Then weight of the body is in vertically downward direction mg. A normal reaction perpendicular to the surface c. mg and normal reaction are in opposite direction. So here also net force or resultant force on the particle is 0. Then this is in equilibrium. See, if you draw a tangent for this elemental section, tangent is parallel to this section. So theta is 0 means du by dx is equal to 0. Again, second condition is satisfied. Okay. See, in this case the body is at the bottom of hemisphere. So we have taken this is a datum level. Height is 0. Okay. Then potential energy means U. Potential energy means U. Potential energy is 0. Because height is 0, this is datum level or ground level, so potential energy is 0. In this case, potential energy is 0. Is it clear? Means here potential energy is minimum since height is 0. But in this case, if you take this is datum level, ground level, and this height is h, then here potential energy is equal to mgh. We may take this is maximum. This is maximum. In this case, potential energy is minimum, but in this case, potential energy is maximum. Again, here also resultant force 0, du by dx is 0. Okay. Then neutral equilibrium, we find conditions. Neutral equilibrium, say this is a horizontal surface and this is datum level, this is ground level. Initially, a body of mass is at this position. Again, this height is h. Again, this height is h. Here also, see, weight of the body in vertically downward direction normal reaction perpendicular to the surface, and here again resultant force is 0 or net force is 0, or normal reaction and weight balance each other, so resultant force is 0. Is it clear? Okay. But here potential energy is again mgh. Potential energy is mgh. See, now suppose this ball is tilted so that it moves to a new position from A to B. Here also weight is mg, normal reaction is R. Here also resultant force is 0, but potential energy is again, this height is h, potential energy is again mgh, means potential energy is constant. Potential energy is constant. Then we will see the other condition. See, here also du by dx is 0, here du by dx is 0, and here also since net force is 0, here also du by dx is 0. See, both the conditions are satisfied. First condition, second condition, first condition, second condition, first condition, second condition, first condition, second condition. So we have discussed the general conditions for equilibrium. Net force should be 0 and slope should be 0. In these three cases, both the conditions are satisfied. Then how can we say all are at the state of equilibrium? But how to define stable equilibrium, unstable equilibrium, and neutral equilibrium? See, that's thing. Suppose this body is tilted a little in upward direction. Just see, I am showing here. This is the initial position. Suppose it's slightly pushed to this position. Just imagine this is ground level. This angle is theta. Then obviously on this body a downward force, means component of gravitational force will be mg sin theta, as you know. For an inclined plane, if this angle of inclination is theta and body of mass m, then downward force is mg sin theta. If the ball is tilted a little, then component of gravitational force mg sin theta will bring it back to the original position. Means if this body is tilted a little slightly, it will again return its original position. So this is the position of stable equilibrium. If a body from this position is tilted slightly along this direction or along this direction, it will again return back to its original position due to component of gravitational force along this direction. This is mg sin theta. Okay, it will bring back the body. Of course, if this body is tilted slightly more, then mg sin theta will bring back the body to this position, and at this position it will acquire inertia of motion and move up, and after some oscillatory motion it will again be stable at this position. But we are considering a small displacement, a small push, then it will return back to its original position, means it returns its original position. So this is the position of stable equilibrium. Okay. Now just see, for this body, I am showing again in rough. This mass is m. Just draw a line tangential to surface. Let this angle is theta. Again, if this is m, this is theta. On this body, downward force is mg sin theta. If this body is tilted slightly, this component will bring back, this is mg sin theta, this is mg sin theta, this component of gravitational force will bring back the body to the datum level. So it can't again return back to its original position. So if once the body is disturbed, If once the body is disturbed, it can't retain its original position, but it will move down. If it is a complete sphere, if it is tilted a little, it will move down, okay, and finally it will come to stable equilibrium, okay. The tendency of body to retain its position at stable equilibrium state, okay. So this is the position of unstable equilibrium, okay. Here potential energy, if you push it, then potential energy increases slightly and comes back to the state of zero potential energy. But here, if it is tilted a little, it will come along the hemispherical path and can't retain its original position. Okay, but in this case, potential energy is mgh at every position. Wherever the body may go, at every position, potential energy is mgh. Then what are the conditions for stable, unstable and neutral equilibrium? See, here du by dx is 0. Du by dx is 0. This is partial derivative. Then d square u by dx square means d by dx up du by dx means a double differentiation. It will come d square u by dx square. See, for stable equilibrium, du by dx is 0, unstable, for unstable also du by dx is 0. For neutral equilibrium, this is neutral, potential energy is always constant. Again, this condition is same. But for stable equilibrium, if du by dx is 0, then d square u by dx square will be greater than 0. This is the condition. This is the condition for stable equilibrium. If d square u by dx square is 0, then this satisfies condition for minimum potential energy. Potential energy minimum if d square u by dt square is greater than 1, greater than 0, then this satisfies condition for minimum potential energy. See, resultant force is 0, potential energy is minimum, then the body will retain its original position, then this is the case of stable equilibrium. Resultant force 0 and d square u by dx square is greater than 0. See, if d square u by dx square is greater than 0, then potential energy is minimum, or potential energy has minimum value, means minima. Then come to this point again, the both conditions are same for any type of equilibrium, but this is unstable equilibrium. How can I prove this is unstable equilibrium? Here, potential energy is maximum, means again du by dx is 0. In this case, d square u by dx square. See, here greater than 0, here less than 0. This is the condition. If d square u by dx square is less than 0, then this satisfies the condition for maximum potential energy, or potential energy is maxima. Potential energy is maximum. Then how to know potential energy is minima or potential energy is maxima? If d square u by dx square is greater than 0, potential energy is minimum. If d square u by dx square is less than 0, then potential energy is maximum or maxima. Okay. Then come to this point. Here, potential energy is constant. du by dx is 0, then in this case d square u by dx square is equal to 0, which satisfies the condition for neutral equilibrium. Potential energy always constant and d square u by dx square is 0. Is it clear? Have it? We have discussed all the conditions. So this is enough and more than sufficient to distinguish between stable, unstable, neutral equilibrium. Again, these two conditions are general conditions for all types of equilibrium. Resultant force is 0 and du by dx or du by dy or du by dz is 0, or in general du by ds is 0. These are general conditions. But for stable equilibrium, d square u by dx square is greater than 0, which implies potential energy is minima. Here, same condition is there, but for unstable equilibrium, d square u by dx square is less than 0, so potential energy is maxima. Maximum potential energy means it is unstable. When it tilts a little, it will come back to, it will leave its position and can't never return back to its original position. And here, potential energy is constant, but all these cases, in this case potential energy changes, here potential energy is constant, and in this case also resultant or net force is 0, du by dx is 0, but condition for neutral equilibrium is d square u by dx square is 0, here d square u by dx square is less than 0, here d square u by dx square is greater than 0 minima, less than 0 maxima, and this is only 0. Is it clear? Then some fundamental numericals on the basis of these three discussions: stable equilibrium, unstable equilibrium, and neutral equilibrium. For stable equilibrium, d square u by dx square 0, potential energy minima. For stable equilibrium, d square u by dx square greater than 0, potential energy is minima. For unstable equilibrium, d square u by dx square is less than 0. If it is less, then potential energy is maximum. This is the basic thought. Okay. Let's have some fundamental numericals, and also we'll have idea on local maxima and local minima. Okay. Just remember all these conditions. Some fundamental and basic numericals, and I hope you will enjoy all these fundamental numericals. Okay. Question number 1, first question. Potential energy U. We may consider any direction, either x or y or z. Potential energy is given as 3x square minus 12x, x, the variation of displacement along x-axis. This is potential energy, means expression for potential energy. Very simple question. Find position of stable, unstable, and neutral equilibrium. We'll see what type of equilibrium we can achieve, stable or unstable or neutral, and accordingly we'll show the position. Is it clear? Okay, very good. This is your question. See, expression for potential energy, answer. Expression for potential energy is 3x square minus 12x. So, for equilibrium, our general condition, resultant force or net force is 0, and another condition, force is equal to minus du by dx is equal to 0. These are two basic required conditions. Then we will differentiate partial differentiation minus d by dx. In place of u, we will write 3x square minus 12x is equal to 0. Is equal to 0. Then what it comes? Minus d by dx of 3x square 6x, d by dx of 12x 12 is equal to 0. Is it okay? Fine. Then 6x is equal to 12. 6x minus 12 is 0, 6x is 12, and x is equal to 12 divided by 6, that's equals to 2. Value of x is 2. Okay. Then the next condition, see, du by dx will have d square u by dx square, means to get the condition for stable or unstable or neutral equilibrium. Okay, let's see what type of equilibrium comes for x is equal to 2. So d square u by dt square dx square, see, this is a formula for du by dx. I am writing here, du by dx is equal to 6x minus 12. Du by dx is 6x minus 12. So similarly, d square u by dx square is equal to, what will come? 6x minus 12. Again we are doing double differentiation. Du by dx, this is d square u by dx square, means d by dx of u. Okay. In place of u, this is du by dx, means this is again du by dx, or you directly do double differentiation. This will come 6x, differentiation of 12 is 0, then it will come 6. It will come 6. See, d square u by dx square is equal to 6, means plus 6, so greater than 0. As we know, if d square u by dx square is greater than 0, if greater than 0, then this satisfies conditions for minimum potential energy. Minimum potential energy means potential energy is minima. If potential energy is minimum or minima, then this position is the position of stable equilibrium. Sorry, greater than 0 means this is maxima satisfies condition for maximum potential energy. So this is position of, if potential energy is maximum, then this shows position of unstable equilibrium. As we have discussed, if d square u by dt square is greater than 0, then this satisfies condition for unstable equilibrium. Greater than 0 or less than 0. Here greater than 0. Greater than 0 means maxima, Greater than 0 is maximum, so satisfies condition for, minimum potential energy. If d square by u by dx square is maximum, then potential energy is minimum. I was right, minimum. This satisfies condition of stable equilibrium. This is minima. Minima means stable equilibrium. D square u by dx square is greater than 0, maximum, then potential energy is minimum. So this is the condition for stable equilibrium. Oh, I know, you have estimated quickly. Very good. Then second question, number 2. Second question. Question number 2. Potential energy U. Potential energy U is given as 27x minus x cube. Potential energy is given as 27x minus x cube. Then we have to find positions of stable and unstable equilibrium. This is expression for potential energy. Okay. So, for all cases of equilibrium, net force is 0. For all cases of equilibrium, du by dx minus du by dx is equal to 0. These are two basic conditions. Again, expression for potential energy is 27x minus x cube. Then we will have minus du by dx. Then this is minus d by dx of, in place of u, we will write 27x minus x cube. Then minus du by dx is equal to minus d by dx of 27x, this is 27, d by dx of x cube, 3x square. Again, minus du by dx is 0, minus du by dx is 0, so we can write this is 27x minus x cube, okay, this is minus, okay, then du by dx is 0, then compare it with 0, minus 27 minus 3x square, du by dx is 0, this is 0. Is it clear? This is 0. Then solving it, 3x square is equal to 27, x square is equal to 9, so x is equal to plus minus 3. X is equal to plus minus 3. Okay. Then see, d square u by dx square. See, we have got du by dx. But in accordance with our form, if d square u by dx square is greater than 0, then it satisfies condition for minima, means satisfies condition for stable equilibrium. So d square u by dt square, d square u by dx square. So what we will do? d by dx of d by dx. See here, du by dx is 27 minus 3x square. Means this is minus differentiation of minus 3x square, means 27. Differentiation of 27 is 0, and this comes minus 6x. This comes minus 6x. See, for x is equal to plus 3. We have got x is equal to plus minus 3, means d square u by dx square is equal to minus 6 into plus 3, that's equals to minus 8. Minus 18 is less than 1. Okay, means here d square u by dx square is minimum. Less than 0 means minimum, So if d square u by dx square is minimum, then this implies potential energy is maximum. If d square u by dx square is minimum, then potential energy is maximum, and this shows the position of unstable equilibrium. So at position +3, we have taken +3, potential energy is maximum. Then for x is equal to -3. This is x is equal to +3. Then x is equal to -3. You see d square u by dx square is equal to -6x, as we got d square u by dx square is -6x, and here d square u by dx square is -6 into -3, that comes +18 greater than 0. Means d square u by dx square is equal to +18 greater than 0. Okay, but here, sorry, not 1, less than 0. This is greater than 0. If d square u by dx square is greater than 0, then this satisfies d square u by dx square greater than 0 means maximum. So this implies potential energy is minimum. If potential energy is maximum, then this is unstable equilibrium. Here potential energy is minimum means stable equilibrium. See, once you understand the concept, then you can find the position of stable and unstable equilibrium. Here x is 3 positive, then this potential energy is maximum, or d square u by dx square is -18 less than 0, then potential energy maximum, and at point 3 condition of unstable equilibrium is satisfied, and here d square u by dx square is +18, so this is maximum means greater than 0, and here if d square u by dx square is maximum, potential energy is minimum. If potential energy is minimum, then this satisfies the condition for stable equilibrium. Okay. Then next one, just have idea about local maxima and local minima. Very important. Just a concept, no numerical. Local maxima and minima. See, our previous discussion, I am combining the diagram. This is unstable equilibrium, this is stable equilibrium, and this is neutral equilibrium. Hemispherical bow. Okay, hemispherical bow. And this is horizontal surface. Here potential energy maximum, unstable, potential energy minimum, stable. Here potential energy constant. Okay, potential energy constant. So this is neutral equilibrium. This is neutral equilibrium. For neutral equilibrium, potential energy is constant. Here also du minus du by dx is 0, but d square u by dx square is 0. This is stable. Sorry, neutral. This is stable. Potential energy minimum. Potential energy is minimum, so d square u by dx square is greater than 0. So this is the condition of stable equilibrium. d square u by dx square is 0 means potential energy is minimum, or you may write it like this: d square u by dx square if greater than 0 or maximum, then potential energy is minimum. Here potential energy is constant, and this is maximum potential energy. d square u by dx square is less than 0 means minimum. So means here potential energy is maximum. So this is unstable equilibrium. Is it clear? Then local maxima and local minima. Just think. And taking a rigid curved path, rigid curved surface. Okay. See, as we have discussed, if a body is placed here, top of this curved surface, then here potential energy is maximum. And if potential energy is maximum, this is the position of unstable equilibrium. And here potential energy is minimum, then this is position of stable equilibrium, and accordingly this is unstable equilibrium. Potential energy is maximum, and here potential energy is minimum, and this is stable equilibrium. Is it clear? And this is a position where potential energy is maximum, then this is the position of unstable equilibrium. But just compare. Let this position is A, this position is A, and this position is B. Just compare. This position is B. So we are observing that at position A, potential energy is minimum, but at position B, potential energy is maximum. See, if you take this is datum level, this is datum, ground level, then potential energy for position A, to get potential energy, this height is h1. For position B, this height is h2. So potential energy at A, at position A, potential energy is mg h1, and at position B, potential energy is mg h2. But as we know, h1 is greater than h2. h1 is greater than h2 means if you compare between position B and position A, then at position A, potential energy is more as compared to potential energy at B. Then if you compare like this, then I may say at B, potential energy is minimum, at position A, potential energy is maximum. But what we have taken here, potential energy is maximum, here potential energy is minimum. Then what is correct concept? Yes, this is a minimum potential energy. Yes, this is maximum potential energy. But if you consider local maxima and minima, for this locality, potential energy is minimum. For this locality, potential energy is maximum. Okay. The practically, if you compare all, then at this position, potential energy is minimum. At position B, potential energy is maximum. But if you consider the concept of local maxima, in this locality at position A, potential energy is minimum. In this locality at position B, potential energy is maximum. But if you compare between A and B, A is at maximum potential energy, B is at minimum potential energy. But in accordance with this concept, local maxima and local minima, this is minimum, this is maximum. Okay. Last numerical and a beautiful numerical. Will enjoy. Very good numerical. I hope you will enjoy this. Okay. We will complete the final part. We will complete the final part. See, I am going to equation. Question number 3. Question number 3. See, in similar way, potential energy is given as 27x minus x cube in x direction. In x direction plus in y direction 3y cube minus 9y. 27x minus x cube plus 3y cube minus 9y. See, previously we are considering only along x-axis. We may consider only along y direction or only along z direction. Here we have combined both x and y direction. Then question is said, find positions of stable, unstable and neutral equilibrium. Find position of stable, unstable and neutral equilibrium again for all conditions for equilibrium. For all conditions for equilibrium, net force or resultant force is 0. du by dx is equal to 0 or du by dy is equal to 0. Okay, because we are considering in both x and y direction. Hey, you are clear or not? Okay, but you are silent in today's class. Very good. So, this is for x-axis, this is for y-axis, general conditions for equilibrium. See, as we have discussed, force along x-axis may be taken as minus du by dx. Force along x-axis, F is equal to minus du by ds. Along x-axis, Fx is equal to minus du by dx. Then this is equals to, again, du by dx is 0 minus d by dx of u. See, in x-axis we have got the expression 27x minus x cube. So we are doing partial derivative. 3y cube minus 9y with respect to x will be 0. So we will take only 27x minus x. 27x minus x cube. Then what will be the result? Minus dy dx of 27x is 27. Dy dx of x cube is minus 3x square. But du by dx is 0. Du by dx is 0. Then what we will get? Means in this case also, if du by dx is 0, then force in x-axis is 0. Du by dy is 0, then force in y-axis is also 0. Fx 0, du by dx is 0. Is it clear? Then we may take here, if du by dx is 0, minus 27 minus 3x square is equal to 0. Then we will get 3x square is equal to 27. x square is equal to 9 and accordingly x is equal to plus minus 3. X is equal to plus minus 3. I think it is very easier for you. X is equal to plus minus 3. Similarly, this is about fx, fy. Fy is minus du by dy, minus d by dy. U, in place of u, will take whatever variables are given in y direction, 3y cube minus 9y. Again, if y is 0 for any equilibrium and du by dy also 0, then minus d by dy of 3y cube minus 9y is equal to minus, this is minus d by dy of 3y cube, it will come 9y square. Then d by dy of 9y is 9. Since du by dy is 0, so 9y square minus 9 is equal to 0, 9y square is equal to 9 and y is equal to, y square is 9 by 9, 1, so y is equal to plus minus 1. What we got from our analysis, in x direction, position of equilibrium, x is equal to plus minus 3. In y direction, position of equilibrium, y is equal to plus minus 1. Okay. Y is equal to plus minus 1, x is equal to plus minus 3. Then we will go to final condition for equilibrium. Stable, unstable and neutral equilibrium. Okay. Have you taken all this? Have you taken all this? Good. We have got this, only we need the equation and these data. See, we have got 4 positions in x direction, plus 3, minus 3, in y direction, plus 1 and minus 1. So accordingly, we will get 4 points, you just see. This is origin, this is x-axis, this is y-axis. See. Point 1, I am writing here. First I am writing here. Point 1. At what point we will get equilibrium? What type of equilibrium we will see. Point 1, see. Value of x is plus 3. Value of y is plus 1. See, this is plus 3, minus 3. This is plus 1 and minus 1. So point P1, we will get 4 points. For point P1, coordinates are plus 3, plus 1. For the next point P2, plus 3, plus 1. P1 is equal to plus 3, plus 1. Then P2, again take plus and this is minus. Plus 3. Then third position P3. Then third position P3. See, now take minus, minus 3 plus 1. Minus 3 plus 1. Then point 4. Again take minus 3, minus 1. Plus 3 plus 1. Plus 3 minus 1. Minus 3 plus 1. Minus 3 minus 1. This is 0, means coordinates are 0, 0. Okay. Point P. Value of x is 3. Value of y is 1. So we will get a point here. This is P1. Coordinates are plus 3, plus 1. Then about point 2, plus 3 minus 1. See. This position is 3 in the x-axis. This is 3. And in y direction, this is minus 1. This position is P2 and coordinates are plus 3 along x-axis and minus 1. This is minus 1, this is plus 1, this is plus 3, minus 1. Then third position minus 3 plus 1. This position is minus 3. Then for P3 minus 3 plus 1, this is plus 1. Just extend it. This position is P3 and coordinates are minus 3 plus 1. Okay. And fourth position is minus 3. Minus 1. This is minus 1. This is minus 1. This is minus 3. Just extend it. This position is P4 and this is minus 3, minus 1. So there are four positions of equilibrium: P1, P2, P3, P4. But what type of equilibrium? We don't know. P1, P2, P3, P4, all are the positions of equilibrium. Because all the basic conditions are satisfied, net force or resultant force is 0 and du by dx or du by dy is 0. But what type of equilibrium we have to determine? Okay, I am showing or discussing only about point 1, P1, and all these 3 points you will analyze and please comment. I am taking P1. Coordinates of point P1 are plus 3 and plus 1. I am analyzing this point whether point 3 plus 3 in x-axis is at stable or unstable, then in y-axis plus 1 is at stable or unstable equilibrium. See, if you take point 1, if we consider x-axis means for plus 3, we know minus du by dx. See, I have erased, but we can do it now. Minus du by dx minus 27x, differentiation of 27x is 27, minus differentiation of x cube is 3x square. Is it clear? Okay. Then du by dx is equal to minus 27 minus 3x square. Minus du by dx is 27 minus 3x square, and finally double differentiation d square by u by dx square. If you differentiate it again, then this will be 0 minus 6x. Okay, then let's take first plus 3. Position in x-axis for plus 3, d square u by dx square is equal to minus 6 into plus 3 is equal to minus 18. See, this comes minus 18. Is it clear? This comes minus 18. Minus 18 means this is less than 0. Minus 3 means this is less than 0. Minus 6 into plus 3, this is minus 18. So minus 18 is less than 0. If d square u by dx square is less than 0, then potential energy is maximum. Then this is the condition for unstable equilibrium. So potential energy is maximum and the position is unstable equilibrium. We have put plus 3, we have taken plus 3, okay. So plus 3, if you take plus 3, then this comes minus 18, So potential energy is maximum and position is unstable equilibrium. Okay. Then another point I will do here. Point 1, we are continuing point 1 for minus 3. For minus 3. Again see, d square u by dx square is equal to minus 6x. Here x is 3. Sorry. Value of x. This is 3. This is value of y. Y is 1. Y is 1. Then for x we have got x is equal to plus minus 3. X is equal to okay. Sorry. Okay. So we have got P is equal to plus 3 at point P1, then P2 at point P2, value of x is also plus 3. For plus 3, we have calculated potential energy is maximum because this is minus 18 less than 0, potential energy is maximum. Okay. Then we have to take y. We have to take y. See, this is for x, this is for y. Then d square u by for 1 is y coordinate, then d square u by du by dy. Minus. Means for equilibrium, force in y-axis is 0. So minus du by dy is 0. So minus d by dy. U. See, u is in y. This is 3y cube minus 9y is equal to 0. So minus d by dy of 3y cube, this comes 9y square minus 9 is equal to 0. Is it clear? Is it clear? Now, this is about writing here du minus du by dy is equal to minus 9y square minus 9, then d square u divided by dy square. See, differentiate, this is minus 9y square, so it will come 18y minus 0. 18y minus 0, but here y is 1, so what we will get? 18 into 1, that is equals to plus 18. This part is separate part, plus 18. Plus 18 is greater than 1, means here potential energy is minimum. If d square u by dy square is greater than 1, potential energy is minimum, then this shows position of stable equilibrium. I have checked the point 1. Plus 3 is value of x, plus 1 is value of y. In accordance with that, we have proved d square u by dx square minus 18 less than 0, potential energy is maximum. So, at plus 3, potential energy is maximum. Potential energy is maximum. At plus 1, this is greater than 1, so here at plus 1, potential energy is minimum. And accordingly, we will check point 2, point 3, point 4, And finally, please comment about point 2, point 3, point 4. Is it clear? Is it clear to you? Okay. This is the end of this lecture. Again in next lecture, we will have some again beautiful, very beautiful discussion and the concept with numerical. Thanks my children. Thanks.